is okay. I can see that many of the questions are repeated, that even I started doubting if this is the same quiz for last week or a new quiz, but I can see many questions repeated. So if you can also try to open the quiz, if okay, if it's not, then it's
Yeah,
fine.
it would be impossible.
Yeah, it will be impossible. It will be a big load on the internet. Let's see. Okay, so the first question is telling us, this is number 1. Okay, this is a screenshot of it. To identify an element from a mass spectrum, given below the mass spectrum of a sample of a known element, like we said last week, choose the number of isotopes above the element. Since you have 2 peaks, then you have 2 isotopes. This is the first peak, first isotope, and second peak is second isotope. If you have more peaks, then they will if you have 3 peaks, it will be 3 isotopes and so on. Calculate the average atomic mass of the element. You know that from the last year that you just have to get the addition of 75% multiplied by the mass, which is 35. So for the first isotope, its abundance is 75% and its mass is 35 AMU. And then add this to the second isotope, whose abundance is 25% and its mass is 37 atomic mass unit. And then we divide this by the total, which is 100. So I'm gonna get an average number between the two numbers, 37 and 35. And because the mass, the abundance of 35 is bigger, much bigger, that's why it's normal for your average to be closer to the 35 than the 37. By calculation, you will just get 35.5. And this is the number that you will see in the periodic table. If you checked chlorine, you will see the mass is going to be 35.45 or closer to that. And that's why this is the mass of the element. Using the mass spectrum and the periodic table gives the chemical formula. Of course, I will go and see that this is in the periodic table, and then I'll keep checking the numbers. I will see the only number which is very close. It's mass, the number. I will look by the mass number for sure. The mass which is closest to the chlorine is 35.5. Now let's go for question number 2. If this is 1 is done, no more parts in 1. Yeah, that was only 1. Okay, question number 2 also is repeated. It says write the electronic configuration of vanadium ion. So vanadium is an easy one. It's a transition element. Transition element, I'll just check it in the periodic table, which will look like that. So let me share the periodic table shortly. This is the periodic table. And then I will share the screen also so we can see it. If it loads, yes, it has loaded, fortunately. Then let's see vanadium. Where is vanadium, Mr.? This is vanadium here. So I'll try to use my periodic table as usual. This is 1, second, third period, fourth period. I need the fourth. Anything ends here is S1. Anything ends here is S2. That's P1, P2. P3, P4, P5, P6, and here is the D block. It starts from D1 until D10. So I have S block, P block, D block. It's called S because any element that's here ends with S, any element here ends with P, and any element here ends with D. What about vanadium? Okay, so I'll start from the beginning, 1S2, 2S2, 2P6, keep going, 3S2, 3P6, 4S2, then I'll go for the D block. So we know that if you are in the D block, you have to minus 1 from the period number. So you don't say 4D, you say 3D. If you are in 5, you will say 4D. If you are in 6, you will say 5D, and so on. So every time you minus 1 number. So that's 3D3. So I don't know, I wrote 6. 3D3. Simple and easy and direct. 3D3. That's a configuration for vanadium. And then when you lose 2 electrons, when you lose 2 electrons, you will lose them from the S. That's why last time we said for the transition metals, it's better to write this one before this one. So let's see. In the transition, better to write the 3D3 and then write the 4S. So this will help you not to forget. So let's write the configuration one more time. We said you are until argon here. We can write argon. We didn't say write the shorthand, but this time only I'm writing it. And then 4S2, and then 3D3. So in the transitions, it's better to write the 3D first, and then write the 4S2. Why I'm doing like that? Because when you remove the electrons, you will not forget that you have to remove the electrons from where? From the 4S first. So start by removing the electrons from the 4S. How many electrons you need to remove? You said vanadium 2 plus. So you remove 2 electrons. So you will cancel these 2 electrons. If you cancel the 2 electrons, you will cancel the orbital. Don't write the orbital empty. Don't write 4S0. You will just write the orbital which is after it, which is 3D3. That's why this is the result. Everything until 3p6, and after 3p6, right? 3d3. Where is the 4s2? It is cancelled out because I removed 2 electrons, because he told me it's a positive 2. Positive means I have removed 2 electrons. So let's see the next one. Oh, why not just, we can just screenshot everything from down here and put it in the file just for the records. So let's just do a screenshot from here and copy it here for our file. Let's try to be faster. There's a lot of questions. So go down here and then screen paste this one. Okay, let's see the next question, if number 2 is done. Number 3, calculate the energy of a photon. This is an easy one also, but still we'll do it again. The equation, as said, is made from E is equal to H frequency. So energy is equal to Planck's constant multiplied by frequency. And you don't have frequency, you have frequency, but you are looking for the wavelength. Calculate the wavelength. No, you need the energy. So you have the frequency. Oh, this is easy, direct. You have the frequency already. 6.11 times 10 to the power 14 hertz. And the H is, this is different from the one that we did last time. And the H, or the Planck's constant, is a constant given in the exam. That's 6 point, oops. I lost the numbers. I lost the number. 6.626 times 10 to the power of negative 34. And we'll just multiply these two by each other. So the unit for this one is joule per second, joule second. And this one is hertz, which is how many waves in 1 second. And I don't need to use the speed of light in anything here. I will just need to multiply these two numbers by each other, because E is equal to H multiplied by frequency. He has given the H and he has given the frequency, so no need to use the C or the wavelength at all. And if we do the math, let's try to use our calculator and see if it works. Let's use the math, and we'll share the calculator also. So this is a calculator. It says that 6 point, let's make a bracket. So 6.626 times 10 to the power of, oh, no, this one, 10 to the power of negative 34, 10 to the power of negative 34, and close the bracket, multiplied by, the other one is 6.11 times 14 power. So the answer is our answer here, which is 4.04 times 10 to the power of negative 19. What did we do wrong? So this is the answer. Yes, hertz and joule per second, and it will be in joule because this one will cancel with this one. So the number here is 4.048, and I need three significant figures. So I will just use 4.05 and write it like that. 4.05 and write it like that. Okay. Let's see the next question. The next question is number 4. So let's see here. Which of the following are the factors that affect the magnitude of the lattice energy? Last time we explained the relationship. We said it is directly proportional with the charges. So what is the charge for the first one? And the second one multiplied by each other, and it's inversely proportional to the radius of the two ions. So the lattice energy is directly proportional with the charges, inversely proportional with the radius. You cannot say it's proportional to the distance between the two nuclei, or it's inversely. You cannot say it's inversely proportional to the electron affinity. The electron affinity is not related at all to this one. Question number 5 is again with the PAS. Is it? Yeah, a photoelectron spectrum of element X. Choose the letter that represents the peak that corresponds to the given feature. So identify the element. Before I identify the element, let me see the PAS. So I have here the nucleus is this side. Why the nucleus is this side? Because the closer you are the nucleus, the closer you are to the nucleus, the bigger your binding energy will be. You have to identify where is the nucleus at the beginning, because if it is reversed, you will mess up the graph. Okay, I will usually start with 1s2, and this is the length of the peak that represents the number of electrons. It says that there are 2 electrons here, and if the second peak has the same height, so it means it has the same number of electrons, and that's normal because we know that this is 2s2. And what comes next is n is 2p6. And since the ratio between the number of electrons here is 2 to 6, means the ratio is 1, 2 to 2 to 6 means 1 to 1 to 3. Again, the height of the peak is represented by the ratio of the number of electrons. So if this is 3 times this one, so it's normal for this peak to be 3 times the height of peak B. What about D? It is the same height as peak A and B, which means that it has 2 electrons also. And that's also normal because that should be 3s2. So everything here makes sense. In order to identify the element, let's see which element has this configuration: 1s2, 2s2, 2p6, 3s2. Let's go back to our periodic table. Our periodic table tells us that this is 1s2, and this is 2s2, and then this is 3s2. Since you stopped at 3s2, so this is your element. 3 because it is in period 3, and s2 means it's gonna stop here. We said this is the group that any element in this group its configuration is going to end always in S2. So this is 3S2. I could have even found this without making the full configuration because I know that any element here finishes in S1 and so on. So if I give you an element that finishes in P5, you will know automatically it will be one of these. And if I told you it is 3p5, automatically you will go for this one because 3 means period 3. So no need for me to even make the full configuration, but just to clarify. The outermost orbital is, since we said that this is the nucleus, so for sure this is the outermost. On the other side, is the outermost shell. Outermost shell contains the outermost orbital, which is 3s2 orbital number d. The orbital that's subjected to the strongest nuclear attraction is, of course, the orbital which is closest to nucleus. Since we agreed that the nucleus will be on this side because the binding energy here is the highest, so it's normal for A to be our orbital that has the strongest nuclear attraction. Next question. The next question is question number 6. It tells us that the first ionization energy of an oxygen atom is O16 is less than that of nitrogen atom. Which of the following statement explains this observation? The normal rule for the ionization energy tells me that as you go in the periodic table from the left to right, the ionization energy should do what? It should increase. The normal rule or the trend, the periodic trend, is telling me that the ionization energy should increase. Yes. So if you are here, this is 1312, let's do 520, then it becomes 899, 1086, 1402, 1681. So as you go to the right, in the periodic table, the trend should be that as you go across the period or in the periodic table from left to right, the trend tells you that the ionization energy should increase. 520, 899, 1086, 1402, 1681. So it always increases, except in two places. This is the places that I have not written. If you notice that I have skipped the two parts. I skipped here and I skipped here. Why did I skip here? Because this is the first place that the periodic table will show an exception. So instead of the ionization energy increasing from group 2 to group 3, it decreases. Here 899, here 801. So the first exception is between group 2 and group 3. In this exception, the ionization energy will decrease, not increase. If you noticed here, it's 899 and here 801. Then it goes back to the normal, increases again. Then it increases again. Then between group 5 and group 6, it drops again. So there are two parts in which the periodic table does not follow the trend. Let's see again. This is the drawing that will explain that. The trend in the periodic table is telling you that there is a trend which shows that if you are in group 1, so this is the group number. Let's say this is group 1, group 2, 3, 4, 5, 6, 7, 8. And this is the ionization energy. So the ionization energy of element in group 1, then to group 2 increased. From 1 to 2 increased. Then 2 to 3, it drops. And then 3 to 4 increase. Then to 4 to 5, it increases. Then what happens 5 to 6? Group 5 to 6, from nitrogen to oxygen, it drops. Then from 6 to 7 increases. 7 to 8 is increasing. So the general trend is that it is what? Increasing. The general trend is saying that across the period, the ionization energy increases, except in two places, which is between group 2 and group 3, and one more time between group 5 and group 6. In these two places, the ionization energy decreases instead of increasing. It goes against the trend. Again, this is not only in period number 2, this is in all periods 2, 3, 4, 5, 6. You will notice that here normal increases, then drops first time between 2 and 3, then increases again, then increases more 102. Then again between 5 and 6, what happens from 1012 into 1000? You don't need to memorize these numbers. This is only to explain to you what is the ionization energy trend. Then it dropped again from 5 to 6. It dropped. Then it goes back from 6 to 7 to increase again. And then of course the last one is the highest one, the noble gas. So only these two places there is increase. The question is asking you, why is this? Why is this happening? Why it does not increase as usual? Why it goes down? Why is the ionization energy? And instead of increasing, it has dropped between nitrogen and oxygen. So oxygen should be higher than nitrogen. No, it is less. The reason is as explained here. The outermost electrons in nitrogen atom is subject to less repulsion than that in an oxygen atom. What does this mean? Let's see the configuration for nitrogen. Nitrogen 7 electrons. So nitrogen is 7 electrons. Nitrogen 7 electrons. That means 1s2 and then 2s2 and then 2p what? 2p what? 2p3. So 1, 2, Hund's rule. Can I put it like that? No, Mr. Hund's rule is telling me put it here, then put it here. This is 2px, 2py, 2pz. Okay. Now what about oxygen? Oxygen is 8 electrons. So it is exactly the same, but in the last period, in the last orbital, there is one extra electron. This extra electron is making too much headache. Why? Because I don't want you. I don't want this red guy. This red guy is making what? Making spin repulsion. So is he a noisy person? Yes. Because if it is not that person, these people will be enjoying their time. Why? Everyone is sitting and sleeping in his own orbital without noise. But when this guy comes, he causes repulsion. So nobody likes him. Nobody likes this red. So it is easy or difficult to remove this electron. It is easy to remove this electron. As if I am taking the opinion of these people. What do you think? Should we keep this guy here or should we remove him? No, please remove him. He is making too much repulsion. We wish that we are like the nitrogen without an extra electron. So it is very easy to remove. That's why the ionization energy is less, because it's easy to remove. And instead of being higher, it is less. In order to explain all this noise in the exam, AP Chemistry, FRQ exam, you have to draw these two and show him that this one is causing spin repulsion. If you don't want to write all this, outermost electron is, the outermost electron is subject to less repulsion than that in oxygen, and say electrons in the double occupied cube orbital are subjected to extra repulsion, you can just help yourself in the exam, draw the two configurations and tell him that this electron in the 2p shows extra spin repulsion. Take care, this is not happening between nitrogen and oxygen only. It happens also between phosphorus and sulfur. That's why sulfur is less. Arsenic and Se, selenium. This is less. Only in this one. So these three, the same thing happens. Group 5, group 6, and instead of increasing ionization energy, it decreases. Of course, the other two answers are not right. These ones, double occupied increases the nuclear attraction. Of course, no. Shielding effect, there is no shielding effect difference, and extra repulsion makes it easier to remove. No. Does the extra repulsion make it easier to remove the electron, the outermost electron? Repulsion by the nucleus. The repulsion is not caused by the nucleus. The repulsion is caused by what? By the electron. The electron. So if this word is electron, not repulsion, it would have been right. Okay. So the repulsion is not caused by nucleus. Repulsion is caused by the new noisy person who is sitting here, and the electrons want to get rid of him. The easiest way to get the full marks in the AP chemistry exam, in the FRQ questions like that, is to always draw the configuration, because when you draw the configuration, examiner will know what you are talking about. You'll show him clearly, this is the one that's making the repulsion. Okay, next question is question number 7. The first ionization energy, generally, the first ionization energy of the elements decreases as we go down a group. Why is that? Mister, when you go down the group, yes, here the ionization energy is 520, decreases, becomes 496, becomes 419, 403, 376. So every time you go down the group, the ionization energy decreases. Yes, the question is to explain why. The ionization energy decreases as you go down, because when you go down, the distance between the electron that you want to remove and the nucleus becomes far. So ionization energy increases down the group. Why? Because the distance between the nucleus and the electron becomes far. The more the electron is far from the nucleus, the easier it is to remove. If the electron is here, it's very difficult to remove it because it's very close to the nucleus. So the ionization energy will be less. But the more you get away from the nucleus, the more it will be easy for us to remove you. Check, imagine that the electron is here. Yeah, it's very easy to remove it. The attraction between this nucleus and the electron is too little attraction. That's why the energy required to remove the electron will become less. That's what will happen. Did I just write increase? I wrote increase. It decreases. It decreases because the attraction is too little. So it is easy to remove the electron. Easy to remove the electron. So the ionization energy is less. The ionization energy is less. Okay. This is the first reason. Yes, sir. This is the first reason. This is what we just explained here. The reason is the average distance between the nucleus and the outermost electron increased. The second reason is there is the shielding effect caused by many core electrons. When you make the electrons that far from the nucleus, it's not just afar. There are many layers of other energy levels in between. So, for example, this is the first layer, second layer, third layer, fourth layer, fifth layer. And every one of these layers has electrons inside. Has electrons inside. What do these electrons do? They are all negative charged. Negative, 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 negative. So imagine that these electrons are negative and these electrons are trying to be attracted to its nucleus. It is the same. This is your favorite singer and is happy singing his song. This is his mic. And he is on the stage. And he's on the stage singing his song. And you are the poor person, very happy and trying to come to here. But mashallah, there is 20 bodyguards or a lot of crowd standing here. The more these people are here, the more core electrons are here, the more difficult for you to come closer to your singer. So these people are increasing the repulsion between you and the singer. So it will be very difficult. If your mother come and wants to take you away, then it will be an easy job because there is less attraction between you and this guy. I don't know why there will be attraction anyway. Okay. So the electron here is sitting and these core electrons are in between doing what? Doing shielding. What if I am not in a group which is down? So instead of being here, I am here at the top. Let's look at the lithium. Let's look at the lithium. The lithium, the distance between the lithium and the nucleus is very small. There is only 3 electrons in the lithium, right? 3 electrons. So there is nucleus, then there is one shield with 2 electrons, and then there is the outermost. So what happened here? The shielding is very small. There is only one bodyguard between you and the nucleus. You can just give him one punch, and then you can say hi to your singer. So shielding is very small if you are up. But when you go down, what happened? Oh, Mister, when I go down, the shielding is increased. There is too many people, leading to weaker attractions between the nucleus and the valency electrons. Memorize this so you can put it very fast inside the FRQ exam after you have understood. So when you go down, the summary, why I have less ionization energy? Because distance increased between me and the nucleus, very big distance, and the shielding is too much between me and the nucleus. Don't say the singer in the exam. The next question is question number 8. Why the ionization energy increases across the period? Mister, across the period, the case is different. There is no shielding. There is no shielding difference. So if I asked you to compare between carbon and nitrogen, these two, there is no difference in shielding. How come there is no difference? They are both on the same period. So the carbon, there is nucleus, there is 2 electrons, there is 4 electrons, and this is outermost. The nitrogen, there is 2 electrons and there are 5 electrons. Can you see the difference between the electron outermost shell and the nucleus? Is it the same? Yes, it is the same. There is no shielding difference. Can you see the difference in distance? No distance difference. So these two factors that cause the ionization energy to decrease down the group is not available here across the period. When you go from left to right, the distance is the same. The distance from the nucleus is the same, and the number of shields is the same. So there is no effect from these two factors. What is the only factor that's making the effect? ايه الفاكتور الوحيد? What is the only factor that causes the ionization energy to decrease or increase? The nuclear charge. The nuclear charge, the number of protons. The carbon has 6 protons and the nitrogen has 7 protons. Which one attracts the electron more? This one. It has 7 protons. 7 protons are much stronger in attracting the electron than the carbon, only 6 electrons. This causes the attraction to be more. So the more you go to the right in the periodic table, the more the number of protons will increase, right? Here I have only 3, here I have 3, here 4, 5 protons, 6, 7, 8. So the more you go to the right, the more the number of protons goes up. Don't say number of protons in the exam. For some reason, they don't like this word. So instead of writing number of protons, write the nuclear charge. The nuclear charge increases. The effective nuclear charge increases. The more you go to the right, the number of protons will increase. The attraction between the nucleus and the electron increases. So it becomes more difficult for the electron to be removed. That's why the ionization energy increases. So the summary of the trend of the ionization energy, when you go from left to right, the ionization energy increases, and when you go down, the ionization energy decreases. Where do you find the highest element that has the ionization energy? Right up. So go right and go up. Here, this is the highest element of ionization energy. Don't talk about the noble gases. They are a different story. Where is the element with the lowest ionization energy will be? Down and left. So this is the element that has the lowest ionization energy. Don't talk about these ones also. They are radioactive crazy elements. So this is the highest, this is the lowest. Okay, let's see the next question. We didn't specify the answers, by the way, في الآخر. The distance between the nucleus and the outermost electrons is similar. This is what we said. The distance and the shielding is similar. You don't say the shielding decreases. No, the shielding does not decrease. The shielding is the same. One shield here and one shield here. If you looked at fluorine or any other element in the same period means same shielding and same distance. the nuclear attractions are weakened. Can you say the nuclear attractions is weakened? It's not weakened, it increased. You have more protons, come on, you have more protons. So attractions are more. The nuclear repulsions are strengthened. What does this have to do with anything? This is the two answers only. So question number 9 is telling us, what are the factors that affect the atomic radius? Guess what? They are the same factors. The factors that affect the ionization energy are the same as the factors that affect the ionization energy. Are the factors that affect the atomic radius. What are they? The nuclear charge, the number of energy levels, and the shielding effect. So take care. These three factors are the same factors that affect the ionization energy and affect the atomic radius, and also affect the electron affinity. They are the same three factors. What are they? Nuclear charge, or the number of protons, number of energy levels, which is the same as the distance from nucleus. If you have more energy levels, you will be farther away from the nucleus. Shielding effect of the core electrons. When you have more energy shells, you will have more people between you and the singer. So you'll have more shields. Spin repulsion, no. Number of very C electrons doesn't matter. What happens in the atomic radius? Mr. The atomic radius, as you go to the right, it decreases. So 167, 112, 87, 67, 56, 48. So as you go to the right, it decreases. This is regarding what? Atomic radius. And when you go down, the number increases. When you go down, the number increases. So you can say that it is opposite to what? Opposite to ionization energy. Opposite trend. The trend is opposite to ionization energy. Ionization energy used to increase here and decrease here. Well, it's right. Let's copy it here on our file also. Okay, next question. Let's try to be faster. Faster. Question number 10. So sodium and chlorine combine to form a white ionic sodium chloride. Knowing that the sodium and chlorine belong to period 3, how do the ionic radius and the atomic radius of sodium compare with those of chlorine? We just explained that when you go to the right, the ionic radius is gonna decrease. So this means that the sodium is bigger than the chlorine. Yes, sodium is bigger than the chlorine. This is the atomic radius. Take care, I'm talking about what? The atomic radius. Did you just write ionic radius, mister? Yes, my mistake. The atomic radius, atomic radius. So we said that as you go to the right, the atomic radius decreases, and as you go down, it increases. So this means that the chlorine is less than the sodium. Okay, so chlorine, because chlorine is on the right side from the sodium. Let's put it here also. Let's put this down here. Come, please. Okay, this is for the atomic radius. The sodium is more, because when you go right, the atomic radius decreases. What about the ionic radius? Is there a difference? Yes. This is the radius of the atom, and this is the radius of the ion. Ionic radius, it's a little bit different. When you go to the right here, the ionization energy is a little bit, the ionic radius is a little bit crazy. It's a different trend, because I see here in the metals, it keeps decreasing. So sodium decreases, here decrease in the metals, as long as you are still in the metal side. Where is the metals and non-metals? This is the metals and non-metals. As long as you are in the metals, these are the metals. It keeps doing what? It keeps decreasing. Then when you go to the non-metals, the ionic radius starts to what? Increase. The more you go towards the non-metals, the ionic radius starts to increase. So this means that it is the reverse almost reverse, because when you go to the right, it increased. When you go to the right, increased. So if you compare chlorine to sodium, you will find the chlorine is more. You will find that the chlorine is more. So the ionic radius has increased, but the atomic radius has decreased. Let's screenshot this one also. And I will just say it again. The atomic radius, when you go in the periodic table from the left, let me write it here, atomic radius. When you go from left to right across the period, the atomic radius decreases. What about the ionic? When you go from the ionic, it has a different trend. First, it decreases in metals. As long as you are in metals, it decreases, then increase in non-metals, then increase in non-metals. So this means that the non-metal, which is the chlorine, was bigger than the metal, which is the sodium. Okay, you must memorize the trend. So this means let's memorize them. Ionization energy, when you go to the right, it increases across the period, and it decrease down the group. The atomic radius, we said that atomic radius is the opposite. So atomic radius, it has decreased across the period and increased down the group. The ionic radius is crazy. Ionic radius is crazy because at the beginning it decreases in metals, then increase in non-metals. So I can just say that general trend is almost opposite again of the atomic radius, or similar to the ionic radius, but I cannot say fully because at the beginning it decreases here. While when you go down, the ionic radius is gonna increase. So generally it's gonna increase either in the metals or in non-metals. So when you go down, it becomes similar to the ionization energies. Very important. So here I will say that it increases down, so it increases down the group. Okay, we know that electronegativity is also the same as the ionization energy. So ionization energy and electronegativity is the same. Also, when it goes to the right, so ionization electronegativity also increases and decreases down the group. So it's very similar to the ionization energy and electronegativity are both similar. Okay, I'm gonna just minimize this if you wanna screenshot it, and said that this is the general trends in the periodic table, general trend in the periodic table. If you go to the exam, you must know this by heart. You must know this by heart, not this heart, mister, the heart in the mind. Okay, next question is, so as we finally agreed about this question, by the way, that the answer is E. Question number 11. Explain the difference in the atomic radius between of elements in the same period. Mister, you just said that when you, in the atomic radius, when you go to the right, the atomic radius decreases. And why did you say that? Where did we write it? We write it here. We said the atomic radius will decrease when you go to the right in the same period. Why is that? Because nitrogen, for example, and oxygen. Nitrogen has less nuclear charge. What is the meaning of less nuclear charge? Means less protons. You just know to yourself that it means protons, but don't write it down in the exam. You just don't write it. Write only less charge. So the number of valence electrons experience a weaker attraction to the nucleus. That's all that you need to know. So since you have less protons, and here more protons, don't say Mr. less or more protons. Okay, less nuclear charge and more nuclear charge. This means that the number of electrons will be attracted by less protons. So the attraction is less. That's why the size becomes big here. Here the number of electrons are attracted by more protons. That's why the size will be less. Imagine that you are attracting the circle so that you are just shrinking it. So you are attracting more as if you are shrinking it, more shrinking. Here I have less protons, so the nucleus is not able to shrink it more. Imagine that the protons are attracting the radius more and more and more. So if you have more protons, it is able to attract more, so shrink it more. That's why its size becomes less. Determine the position of the element in the periodic table using its electronic configuration. We say that it is 4p5. Mister, I know that p5 means anything that's here automatically. And if he told me that it is in period number 4, how did you know? Because he wrote 4 here. That makes the things very easy, because I can just go to the periodic table and see where is period number 4, and then go here. Then automatically I will know that it is a bromine in 1 second. So it is in group number 7 or 17 and in period number 4, which is our answer. D is our correct answer. 4 and 17. So this is our answer. Okay, element X is unreactive and is in period 5. What is the correct shorthand electronic configuration for element X? Oh, element X is unreactive and in period 5. This is period 5. The first thing that comes to my mind when he talks about something which is unreactive is noble gases. Yes, noble gases are the most elements that are unreactive that I know about. So 1, 2, 3, 4, 5. You said they are noble gases. So you are talking about these ones, this color. So 1, 2, 3, 4, 5. I am xenon. What is your configuration? I will end with P6. How did you know that it ends with P6? Anything that's here ends with P6. Anything here P5. Anything here P4, and so on. Okay, what is the question? Find its electronic configuration, but using the shorthand configuration. Shorthand configuration, we said you have to go to the previous noble gas. So keep walking left, 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 until you start to meet the first noble gas. The noble gas that I met here, Mr., was krypton. So this is krypton. I will write krypton here. And then you continue the configuration of the krypton. Krypton, and then what do you say? 1, 2, 3, 4, 5. So 5s2. 5s2. Okay, 5s2. Where is 5s2? At the beginning of the session, we said that it's better to write the D before the S. So don't write the S before the D. Better to write the D before the S. And we said this helps you in canceling the electrons. So let's write. So, Mr., you don't want me to write 5s2 and then write the D? No, write the D before the S. So you said that if you want to write D, don't write 5D. In D block, always minus 1 number. So you want me to write 4D. Okay, 4D. And then 4D, what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, we are continuing until xenon. So 4D10. He wants me to write the D before the S. So 4D10 before writing the 5s2. And this is very helpful, because if I want to make an ion as we agreed, you will remove the electron from who first? From the 5s before going to the 4D. So always, if you want to remove electrons, you will remove it from here first. Then you go to the p orbital. Don't forget, when you go to the p, you will go back to number 5 again. So only you minus 1 in the D. But when you go to the p block, this is the p block. When you go to the p block, you minus 1 again. You return the 1 again. So it is 5p. 5p1, p2, p3, p4, p5, p6. All noble gases ends in p6. That's normal. And it's in 5th period, so it is 5p. So what is my answer? My answer is 4d10, 5s2, and 5p6. The last question before our break is question number 14, and that's luckily an easy question. It says, okay, thorium has a 7 naturally occurring isotopes. Thank you. Which of the following are true about the isotopes? I can answer this if I am in grade 1. They have the same number of protons. They have different number of neutrons. They have the same chemical properties because they have the same number, as they have the same number of electrons. They have the same physical properties. Who said that? Nobody said that. Okay, let's take a short break and come back after 3 to 5 minutes just to drink some water before we can continue. Thank you. Okay, Bismillah. Let's continue our questions. We have stopped here and say Bismillah. This is a question we stopped at number 14. So let's see question number 15, same files that we are sharing. Share 3. In this question, naturally occurring boron is composed of two isotopes, boron 10 and boron 11. What is the average atomic mass of boron? Mister, that's very easy. If you want to calculate the percent abundance for each, you just have to make the equation that we all know. The average is 10.81. That should be equal to the abundance of the first one, which I don't know. So that's why it's called X. And I multiplied by the mass, which I know that it is 10. So 10X plus, yeah, that was the first isotope. What is the second isotope? It is 11. It's 11 AMU. So this means that 11 is multiplied by what? If the total percentage of both of them is 100% and one of them is X. So the total is 100% and one of them is X%. The other one normally will be 100 minus X%. That's why I multiply 11 by 100 minus X. And this all will be divided by the 100. I don't need to tell you what happens later, but if you are interested, 100 multiplied by 10.81 is equal to 10x, and distribute this to like a good math student. So plus 100 multiplied by 1000 is 1100s, and then minus 11x. If you are good at math, you will do this better than me, because this is 1810 equal, if I'm not wrong, yes, 12, is it? 1810 equal to 10x minus 11x. And then, because we don't have too much time and I'm not that strong in math as you, I will just go to see that the answer came out as x is equal to 19. And since the one of them is 19 and you said the other one is 100 minus x, so the other one will be 100 minus 19. That's equal to 81%. So it turned out that one of them is 19%. So the other one is 100 minus 19, which is 81%. That's the abundance, or how much every isotope is available in nature. So if you counted all the atoms of boron in nature, you will see that 19% of them weighs 10 AMUs, while 81 of them percent weighs 11 AMU. The next question, number 16, drag and drop the correct item to name each orbital. You know that the s orbital looks like that, spherical, and the p orbital is dumbbell shaped. And this year they have decided to add the shape of the d orbital as well. So this is the d, that's the s, and that's the p. Question number 17. I don't know, hang it. 17 is asking, choose the correct answer to complete the following. Removing one s electron from oxygen atom requires more energy than removing one from a nitrogen atom. And here the confusion comes. Please focus very well. When he is asking you about removing electron, like we said last time, removing electron from outermost shell, this is talking about ionization energy, which is totally different from this question, because he is not taking electrons out from the outermost shell here. He's taking the 1s. And 1s is not the outermost, it's not valency. This is core. So if he's talking about core electrons, take care and open your eyes. This is valency, and valency is not what I'm asking for. I'm talking about core electrons. Mister, why is the difference? The difference is that we just said that there is an exception between the oxygen and nitrogen, and said that instead of oxygen becoming more, it becomes less. So the oxygen actually is less than nitrogen in the ionization energy. While in the core, removing one s electron from the oxygen is requiring more energy. So let me write it in green. This means that it is actually more, not less than nitrogen. Did you see the difference? Here, this one is less because this is an exception to the trend. But this is not related. Let me write everything here in green and everything here in red. This is not related to ionization energy. This is only one s electron, and this one s electron is very close to the nucleus. This is the first energy level, right? Very close to the nucleus. So the only thing that will determine if the electron is attracted strongly is weakly is what? The nuclear charge. Forget about the spin, forget about everything else. The spin does not make difference here. This one does not make difference here. Why? Because I'm not talking about all these things. I'm just talking about an electron here. The electron here, if you want to remove this guy, the only thing that makes it attracted to the nucleus or no, it's very close to the nucleus. This is the first energy level. So the only thing that makes it less or more attracted is the number of protons. Who has more protons? Oxygen. Who attracts the electron more? Oxygen has 8 protons. That's why it becomes more difficult to remove the electron from the oxygen than the nitrogen. That's why the answer says here is oxygen is bigger than nitrogen. Please take care. This is totally different and the source of confusion. Oxygen is more than nitrogen because this is 1s, not valency electron. Below is the complete photoelectron spectrum of a pure element X. X is, where is the biggest binding energy? The binding energy is bigger here. It's -16. -16 is bigger or -19? Of course, -16 is bigger than -19. So here is bigger, so the nucleus is here, mister. So that's 1s. 1, 2. The ratio is 2. 1, 2. Here, 2 electrons. So that must be 2s. 1, 2, 3, 4, 5, 6. The ratio is 1 to 1 to 3. So that's 2p6. Doesn't make to take much smartness to know that this is 3s2. And if this one is half this one, and this contains 2 electrons, so this should be 3p1. That's very easy, mister. The ratio is 1 to 1 to 3. 1 to 1 to 3 to half. So that's 2 electrons, 2 electrons, 6 electrons, 1 electron. So 2 electrons, 2 electrons, 6 electrons. Did I miss 2? Yes, this one, 2. I did not write. There is actually a 2 here and 1 here. So the ratio is 1 to 1 to 3 to 1 to half, means 2 to 2 electrons, 2 electrons to 2 electrons to 6 to 2 to 1. Okay, that's the correct answer of element X. And what is the element X? Let's go to the periodic table and check which element has this configuration. What ends in 3p1? Doesn't take much time to know that 3p1 is gallium. Is it? Okay. So the element is aluminum. Why is aluminum? Because, mister, you are talking about 3, and here you are talking about 4. So either you need new glasses or new better glasses. Okay, so that's 1, 2. He said 3 here, so you are not talking about gallium. You need talking about aluminum. Aluminum, mister, is what's in 3. Gallium is 4. So the correct answer, of course, is aluminum. Forget my glasses. It's not me, it's my glass. Write the shorthand electronic configuration of the following ions. Let's do this fast as we can. Every time you say fast and you are slow. Titanium. Let's go titanium. Let's go titanium. And it's not normal titanium, it's titanium 2 plus, so an ion of titanium. Okay, so let's see titanium. Titanium is here, mister. So this is 1, 2, 3, 4. 1s2, 2s2, 2p6, 3s2. I don't need to do this. I'm asking for the shorthand. Oh, so go left until you meet the first noble gas. Left, 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 left. Here is the first noble gas that you meet. Write it down in brackets AR, and then that's 1, 2, 3, 4. Continue in 4. 4s2. Mister, you said you will write the 3D first. Oh, I forget. So write the 4s2 here, and then titanium. Where is titanium? This is the one. So 3D1, 3D2. That's 3D2 titanium. Mister, you need to remove 2 electrons. Why? Because he said 3D titanium 2 plus. So remove these 2 electrons. So the configuration is simply AR3D2. Thank you. What about phosphorus 3 minus? If I do the same thing here, I will say that phosphorus 3 minus. So this is phosphorus 3 minus. So I'll go again. Noble gas is go left, 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 left. You meet the neon, first one, neon in brackets. This is the shorthand. After this one, you start 1, 2, 3. So that's 3s2, 3s2. There is no p here. So 3 p1, p2, p3. So 3p3. Wait, did you add electrons? Yes, I added 3 electrons. How many did you add? 6. So 4, 5, 6. You are talking about here. So it is 3p6. When it gains 2 electrons, it becomes stable as the argon. That's why the configuration is 3p6. Next question, number 20. Which of the following are true about 2px and 2py? Are they staying in the same energy subshell? Yes, they are. That's why they are known as degenerate orbitals. They are all in the same energy level. Degenerate means they have the same energy. They have the same energy. Why they have the same energy? Because they are in the same subshell, which means that they are in the same shell, by the way. They have the same energy and sublevel. They are at the same energy but different sublevel. No, they are hybridized. Who said that? They occupy the same subshell but in different energy level. That's completely crazy. Number 21, identify a free radical element. Last time when we checked fluorine 9, we said that it is 1s2, 2s2, and then how many electrons do you still have? I have 5 more. So I have 5 more electrons. Then go and put in 2p6. How do you put according to Holmes? The guy stays here. Assalamu alaikum. I have 1 more electron, put it here. I have 1 more electron, put it here. So how many are now? 7, and I have 9. So 2 more. I don't have any chance. I'll put 1 here and 1 here. If there is one free unpaired, it's not free, it is unpaired orbital. Unpaired. What is the meaning of unpaired? It means it has 1 electron inside it, not 2 electrons. If it has 2 electrons, it's called paired. If it is unpaired, then it is called what? A free radical. So the element that has an orbital with unpaired electrons, meaning not 2 together, it's called a free radical. When we checked the other 3 last time, they were not free, so you can do it yourself. The Cl minus gains an electron and becomes like the argon. Do you think the argon has free electron? No, mister. Any noble gas ends with B6, and since it ends with B6, so I'm sure that it will look like that. I'm sure that it will look like that. 1, 2, let me draw with this one. 6 means 1, 2, 3, 4, 5, 6. Is it unpaired or paired? They are all paired. Paired means that it's not free radical. Not free radical. The potassium does the same. When it loses 1 electron, it becomes like the argon. Same. Neon is noble gas. Anything noble gas has for sure 6 electrons in the P6. That's why it will never be a free radical. Question number 22 gives the full electronic configuration for the following. Na plus is 1s2, 2s2, 2p6, 3s1. When you lose 1 electron, then you remove this and you become 2p6 only. P3 minus, we just explained this few seconds ago. What is the correct electron in box configuration of the lowest energy level for the oxygen atom? Last time we said that this is right. That's wrong. Why this one is wrong? Because it's crazy to put 1 electron here. This should not be here. It should be here. That's wrong, and this is right. These 2 people are crazy because they are sitting here and leaving this room empty. They should not be like that. They should look like that. They should not be like that. They should look like that. 1, 2, 3, 4. So 1, 2, 3, 4. What rule says that? Hond's rule tells us that you should not start pairing electrons unless you put separate electrons in the separate orbitals first. This guy is also crazy because these people decided to stay here and this is not done yet. It should be also not like that. It should also look like this guy. And here it's not correct. Why it's not correct? Because for some reason he decided to forget about 2s2 electrons. He put one s2 and then 2p6 directly. But what about the 2s2? So that's also wrong. These all are wrong, and the correct one is A. And the next question is asking, since this one has unpaired electrons, where are the unpaired electrons? This is unpaired. This is unpaired. So it's going to be called free radical. Is this a free radical? Yes, it is. Where is part B from the question? I don't see it. Last time it was called ask it, but this time I don't see it. Question number 24. Consider MGX where element X is in period 4. What is the electronic configuration of X? Kind of difficult question. No, it's not difficult. Mister, you said it's MGX, right? Let's investigate. MGX means it is magnesium, and I know magnesium is in 2+, and X is in period 4. Mister, if this is 2+, and there is no charges here, so I know for sure, because I'm very smart student, that this should be 2-. And right? Yes, that's why they canceled out. If it is 1-, then the compound will not be MGX. It will be MGX2. If this one was 3-, it will be MG3X2. If this was anything else, the compound will not be MGX. The only thing that makes the compound MGX is that this should be 2-, because in this case, these two will cancel out and the compound will be MGX. What is the benefit of knowing that this is 2-? The only orbital, or the only group that becomes 2- is group 6. We know that group 6 is the only group that's always 2-. So I know that it is in group 2 now. Very good information. So if you know that it is in group 2 and it is period 4, so it's very easy to locate the element. Yes, it is in group 1, 2, 3, 4, period 4, and group 6. So this is selenium. What is the configuration of this guy? 1s2, 2s2 until it ends with P4. We know that anything in this group ends with P4. P1, P2, P3, P4, P5, P6. So this one ends with P4. Before the P4, there was the total 3D. I guess you know how to do this. I guess, and I wish. Okay, the surface of a metal is struck by electromagnetic radiation. Electrons are observed to be emitted because energy is equal to H multiplied by frequency, and I don't have frequency here. I need the wavelength. So E is equal to HC over the frequency, this one. So can you get this one? Yes, E multiplied this guy is equal to HC. So this guy is equal to HC over E, and you should do the rest. Find the wavelengths, and wavelengths, the answer will come in meter. Why is it in meter? Because the C that you have used contains meters. Don't forget to multiply by 10 to the power of 9 to get the answers in nanometer, which will be 475. And if the answer is 475, what is the color that you imagine? The only range that contains 475 is this range. So the color that we need is blue, which is the correct answer. Next, no, yeah, it's already blue, which is the correct answer. The next question is that choose the subshell that can accommodate a maximum of 10 electrons. The S subshell accommodate a maximum of 2 electrons. The P subshell accommodate a maximum of 3 orbitals, so 6 electrons. The D subshell contains a maximum of, it has 5 orbitals inside. So it has a maximum of 10 electrons. And the F subshell contains 7 orbitals. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So it contains 1, 2, 3, 4. Oh, let's go with the 1, 2, 3, 4, 5, 6, 7. 8, 9, 10, 11, 12, 13, 14 electrons can be accommodated in F. This is D in 10 electrons. Next question is 27. Mr. Bohr, his experiment proposed that the electrons orbit the nucleus in a specific circular path. The model below is used in the quantum mechanics as its hypothetical representation of energy levels in the atom. Okay, first energy is n equal to 1, second is 2, third energy level n is equal to 3, fourth energy level is called n equal to 4, and this is my nucleus. The maximum number of electrons that can occupy the fourth energy level can be calculated from this equation. If we want to know the maximum number of orbitals in any subshell, in any shell, it's equal to n squared. And the number of electrons in any shell, the rule is 2n squared. So if you are talking about the fourth energy level, so just remove the n and put 4 and keep these two numbers together. 4 squared is 16 and 2 is equal to 2 multiplied by 16 is 32 electrons can be in the fourth energy level. What do elements in the same group contain? Mr. Elements in the same group, like the group we were talking about now, let's say group 6, for example, they all react in the same way. All these guys react in the same way. If you notice, oxygen loses 2 electrons, sulfur, gains 2 electrons, gains 2 electrons, gains 2 electrons, gains 2 electrons. If you see even the compounds that they make, it's very similar compounds. This is H2O. This guy make H2O. So the sulfur looks, oh my God, that's very nice compound. Let me make the same. Let me make the same. H2S. So H2O, H2S. The selenium. Oh, I like this too much. It's very nice. So they are all reacting in the same way, even making the same compound, H2SE. So all elements in the same group react. They have the same chemical reactivity, and they all contain 6 electrons in their outermost shell. So the number of valence electrons is the same as long as you are in the same group. Why the second ionization energy of sodium is much larger than the second ionization energy of magnesium? This is the trend. You cannot go against the trend. You can in 2 exceptions, but the normal trend tells you that across the period, you have more protons. You have more protons. But Mr., is this an exception? No, it's not an exception. The second ionization energy actually is not talking only about the trend, but when you try to remove an electron from Na plus into Na plus 2, what happens? It will ask you, are you crazy? Yes, because here I'm very stable. I'm like the noble gas man. Why do you want to remove electrons from me? If you want to change from 2,8 to 2,7, you didn't study anything in chemistry, because 2,8 is 100% stable like the noble gas, while 2,7 is nonsense. It doesn't make any sense. So please don't come here. That's why if you try to come here and remove an electron, the ionization energy becomes very big, much larger. While in magnesium, it makes sense, yes, because if you change from magnesium plus 1 into magnesium plus 2, you are changing from 2,8,1 into 2,8. And 2,8, of course, is much stable because this is the electronic configuration of the noble gas. So that's perfect. That's why removing the second electron from the sodium does not make sense. That's why it's very big. But in magnesium, it makes sense. That's why it is smaller. The next question, why is the second ionization energy of an atom greater than its first ionization energy? Yes, because if you want to remove the first electron, usually you're removing an electron from what? This guy is neutral atom, right? You are a neutral atom. If you want to remove an electron from a neutral atom or remove electron from a negative, from a positive ion, which is easier? Which is easier? If you, of course, removing from electron from a neutral atom is much easier. Let's imagine you have a magnet, and this magnet is negative, is positive here. So this magnet is positive here. And this is nothing. This is neutral. This is 0. Which is easier? Take this one away from this guy, or take this one away from this guy, that's much easier because there is no attraction here between the neutral and the negative. While here there is strong attraction between the negative and the neutral. This is strong. That's why it is harder to remove this electron. So removing the electron from the positive ion is more difficult than removing the electron from the neutral atom. That's why it's always harder. The second ionization, IE2, is always bigger than the first ionization energy because the effective nuclear attraction increases. The number of protons here is 12 protons on 12 electrons, while here is 12 protons on just 11 electrons. So we have more nuclear charge on less number of electrons on the remaining electrons that's contained. Number 31, first ionization energy of gallium is less than that of calcium. Let's see the trend. Gallium and calcium. For sure, that's, let's see the ionization energy of gallium here is less than that of calcium. This is 579 and calcium. Why is that? You forgot the trend. We said that there is exception between 2 and 3. That's why it is less. Not only beryllium and boron, magnesium and aluminum, calcium and gallium. Always the third is less than the second. If you remember, we said between 2 and 3. And 5 and 6, 2 places. Don't forget these 2 places where the trend goes down suddenly instead of going up. In all the trend, where is the trend? In all the trend, it should be, the general trend is that it's going up. Only in these 2 places, between 2 and 3 and 5 and 6, it suddenly drops. It suddenly drops. But the rest of the groups, between the rest of the groups, it goes down. Okay, and what is the reason behind that? As per the explanation of the question, where is the question? The reason is that the outermost electron in gallium is less penetrating towards the nucleus, so it's subjected to more shielding by the 4s electron and less nuclear charge compared to the outermost electron in a calcium atom. Mr. I remember now that I explained the difference between 5 and 6. Why there is more repulsion here in this one? That's why the oxygen is less than the nitrogen, but we didn't explain the reason why the electron in the third group is much easier to take than the electron in the second group. So in the second group and third group, why there is drop in the ionization energy? The reason of the drop is that it's easier to remove this electron. Let's see, the electron in the second group looks like that. Let's see beryllium and boron. So beryllium has 4 electrons only, 1s2, and then 2s2. So there's just 4 electrons. And in the boron, there is 1 electron which is in 2p1. 2p1. 1 electron only. Of course, it is much easier to remove this electron because these are all 4 electrons. So the outermost electron in the gallium, which is here, this is gallium and this is calcium. The outermost electron, but in this case, it will not be 2, it will be 4. So 4p1, and this will be 4, and this will be 3, and this is 3. So this outermost electron is less penetrating, it's outside, it's sitting outside towards the nucleus, while this is more penetrating. These are more penetrating. This is less penetrating. Less penetrating means away from the nucleus. So it's subjected to more shielding. Do you remember the bodyguards? There is more shielding between this electron, between this guy and the nucleus than this guy by the 4s. So there is more shielding by the 4s electrons and less attraction. It is farther away from the nucleus compared to the outermost electron in the calcium. Okay, so there is more shielding. The shielding between this guy and this guy is more than this guy in the calcium. Again, you have more layers, more shielding. So there is more shielding and it is less penetrating. Please memorize this very, very well. It's a very easy mark in the FRQ. I'll make summary also for you and send this for the things, the expressions that you need to memorize. If you remember from the last year, the easiest way to know which group you are in is to write like that. Write number 1, 2, 3, 4, 5, 6, 7. The question simply tells you which group I am in. we said that you need to check where is the biggest jump. Here I multiplied almost by 2 from 450 to 920. Then I almost multiplied by 2 again. Yeah, say 1,800 almost. So here multiplied by 2. Here from 1,633 to 600,430, there is almost multiplication by 4. Imagine that this is 1,600 multiplied by 4. That's almost 6,400. So this time there is a very big jump. So take the two numbers between, in which there is the biggest jump between this guy and this guy, and take out the left number, because this will be your answer. You'll be group number. If the biggest jump between 6 and 7, take these two guys out and take the left number, so it will be group 6 like that. So the answer method is find the two groups between there is the biggest jump, take the left one, it will be your group. So there is a great difference between the ionization energy values corresponding to the valence electrons and those corresponding to the core. 33, compare the size of ions. We said that when you go between calcium and potassium and chlorine, so this is calcium and potassium. Let's go for the ionic radius here to explain. This is the ionic radius. So when you go for calcium and chlorine, chloride of course, and potassium ions, you will know that when you go to the right in the metals, it decreases. That's why calcium is less than potassium. That's why calcium is less than potassium. Because in the metals, when you go to the right, the ionic radius decreases. But when you go to the non-metals, what happens? It increased. That's why the chlorine is the biggest one. That's why the chlorine is the biggest one. Again, remember, this is very easy to understand. When you go from the left to right in the non-metals, it decreases. But when you go to the non-metals, it will increase. That's why the chloride is the biggest one, while the potassium, you went right in the calcium. That's why calcium is the left. The rule again is when you go in the metals, as you go to the right, the ionic radius will decrease, but when you go to the non-metals, the ionic radius is gonna increase. That's why the chloride had the highest ionic radius. Atomic radius increases from right to left and down the group. We already explained the trend, and that was our last question. Let's close the recording.